Good afternoon, everyone, and welcome again to the 2020 Virtual T-Cubed International Conference. Again, my name is Eric Butterbaugh, and I'm a member of the T-Cube Professional Development Team. And while we're certainly disappointed not to be together today in person, we are excited about this afternoon's online sessions, and we appreciate you being with us virtually. We're excited about the upcoming session that Stacy Thibodeau is going to be presenting. It is going to be focused on STEM investigations with a 3D twist. And before I pass it over to Stacy, I just want to make a note about the chat window. So we encourage everybody to share your ideas and thoughts via chat. And please be sure to select all participants. That way all of us can see it. And so with that, I'll pass it over to Stacy Thibodeau. Stacy is a T-Cubed instructor from Youngsville, Louisiana, and I'm definitely excited to hear about her STEM investigations with a 3D twist. And with that, I'll pass it over to Stacy.
Can everyone hear me?
Loud and clear. Thank you.
Okay. So thank you guys all for joining. I'm super excited for these 12 sessions today. If you're not able to see all of them, or the ones maybe you wanted multiple, they will be recorded. So that's actually, you get really good information, and then you can play them back at your leisure, and then maybe use them, as a library or share with your colleagues at your school. Like Eric mentioned, I am a T-Cubed instructor. I am a classroom teacher. I teach in Youngsville, Louisiana, which is kind of south central Louisiana. And I teach chemistry and chemistry 1 and chemistry 2. I started using TI products in my science classroom in about 2012. I was first introduced to the TI-Nspire, and I haven't looked back. I strive to make learning visible for students, make learning as easy as possible, but also as connected to the real world as possible as well as the new standards across the country. Louisiana adopted their version of NGSS about 2 years ago, and I sat on the committees for my district and found that TI technology made the transfer from old standards to the new standards seamless. And so I just wanted to share this activity with you guys just to kind of show you how TI technology can help certain parts of the new standards, and show you how a phenomenon-based instruction, maybe an entire cycle would look in a classroom, and then also kind of give you some resources to help you if you're new either to NGSS or new to TI technology. So here we go. First thing is, if you're not familiar, TI has developed 4 lessons that are NGS 3D learning aligned. These 4 lessons have been created by classroom teachers, and these classroom teachers created one strictly biology with nanotechnology and cancer. The biology homeostasis could be some chemistry, physical science, as well as biology. There's a physics one about designing a better helmet, and here's the one that we're going to talk about today, making ice cream. Each of the activities has all the downloadable files. There's TNS files that are associated with it, and if you're new to TI Talk, TNS file stands for a TI-Inspired file, which would be run on the teacher software or the student handheld, and also what's called a template. And so I just wanted to show you real quick. We came up with a template to help anyone who is trying to transition to their new standards, to make it where it's seamless in what the teacher is doing, what the student is doing, and how to connect the wording of DCIs, the disciplinary core ideas, cross-cutting concepts, the CCCs, and then the SEPs for the science and engineering practices. So this document allows for the teacher to have a way to actually go through that. And each of the 4 lessons have their forms or templates to actually guide you if you're trying to find one that would be a good model for you. So I did want to point that out, that those four lessons are there.
And if I may, we're not seeing what's on your screen right now.
Okay.
And to do that, if you go up to the share window and share your screen.
Thank you. Sorry about that, everyone.
There we go. Nope, we're all good. Thanks so much.
I'm sorry. I was a baseball mom this morning, so I had other things going on at home. So what I was showing was this, the website, the education.ti.com website that has the NGSS aligned activities. That there are 4 different lessons that are created by teachers. And then what I was mentioning was the template, and this is what the template looks like. So it's not overly cumbersome. It's easy to adapt to something that you've currently done. Maybe your district provided you a curriculum or curricular materials, but wanted to kind of follow a format of maybe what we did at TI. So in Lafayette Parish, state of Louisiana, we are really big into the 5E model of lessons. And if you're unsure of the 5E model, the 5E model looks at how an entire lesson cycle would work. So we do something to engage our students into the concepts that we're willing to cover, ready to cover for the day. Then there's some kind of an explore. This should be student-driven, could be a simulation, could be a lab, maybe it's some articles you want the students to read, maybe it's a demonstration the teacher does in front of the classroom. Today we're going to see 2 different explore activities. Then there's an explain, where it should be the students doing the explaining first. Students explain what they learned. Teacher is there to maybe clear up any misconceptions, and then teacher solidifies all that information with the actual, like we want to say, notes or the actual validity of the content that was discussed. Some kind of an extension or elaborate, some people call it, that would be where you take it the step further. Maybe if they did a simulation, now you do a lab. If it was a demonstration, now they do a lab. And then obviously with evaluate, that's however the teacher sees fit doing an evaluation. And so what I want to do and what I really try to do is model what happens in my classroom. The students seem to respond to it. When I do the presentations, teachers really respond to it as well. And I don't know, I enjoy sharing what happens and what works in my room. So hopefully you can have some of that takeaway today. And then I'm always available if you have any questions or maybe you have ideas for other lessons and you want to see maybe how I've done it. So with the new standards, there has to be a phenomenon, so some phenomenon-based learning. And so our phenomenon that we're going to discuss today has to do with why do we, which the picture on the left may be unfamiliar to some of you. Here in South Louisiana, we do this pretty much all summer. This is a homemade ice cream maker. And so the phenomenon is, why do we put salt around the ice or in the ice when we're making homemade ice cream? We also do what's in the middle picture. We put salt in our water when we're boiling water for pasta or when you're making rice. And then this top right picture, which is unfamiliar to my students, I had to explain what the picture was. But why do we put salt on icy roads during the winter? So we would start out the conversation. This would be my engage. I would have a poster up and the students would have driving questions where they would ask, why do we do that? And then what can we do to figure out why we do it? One student usually, when this starts, is, why don't we use sugar? And so we have conversations about what kind of compound sugar is versus salt, and what kinds of salts are used when we're doing icy roads versus what we're doing with ice cream or pasta. So then I actually have my students jump into an investigation. But I did go through a slide I wanted to come back to. This slide is this standard that we're covering. Each district, you have your guidelines of what and how you have to unfold your standards. And so I'm not telling you what you need to do. I always go back to NGSS. Even in my state, I think the language of NGSS on this document is helps me figure out what I'm supposed to do to teach it. So this standard is to plan and conduct an investigation to gather evidence to compare the structure of substances at the bulk scale to infer the strength of electrical forces between particles. Huge, huge concept. This is my unit 2 in my lesson curricular sequence, and I'm about to finish it. Well, I was until they closed our school, so we'll see. But this entire activity can be focused on the last part, which is the strengths of electrical forces. And so that's going to be my overarching focus today. So first thing I have my students do is jump into and explore. We know a lot of science, we as a human race, because we are around it all day long. The best part about that is students come to our classes with lots of information, and they come with lots of misinformation too. So part of my task as their chemistry teacher is to make sure I fix those misconceptions. And one of them has to do with temperature and energy. So I'm going to talk a lot about temperature and energy. Energy is one of the cross-cutting concepts that I think in a chemistry classroom or a physical science classroom, middle school science, you can hamper on when you're talking about temperature and phase changes. So the first thing that we do is the Fahrenheit and Celsius temperature scales conversion. When I first started teaching chemistry, I was a good teacher. I wasn't a good facilitator of learning. I taught the material. I didn't facilitate the learning of the material. And I think that is probably the number one, if I was a marketing person, point that I would make with TI technology. So what I'm going to show you today is I didn't teach a thing when I did this activity with my students. They figured out everything themselves. We had the conversation, and then they learned the information. So I'm going to jump to the teacher software. I do want to point out a few things that's on this slide before I move on. So what we have on the right is a TI-Nspire CX that is plugged into 2 temperature sensors, and so that's what we're going to use for this activity. The middle is what the front page of the TNS file looks like. That's what I was talking about a while ago, the TI-Nspire file. That's downloadable from the website. And then over here on the left is the teaching tool that I use pretty much daily, and it's called the TI-Nspire Navigator System. And so the Navigator System consists of these little yellow hats and this wireless access point. So these little yellow adapters make a wireless, like an internet, like a Wi-Fi, connection between this access point and the teacher computer. It's teacher to student and never student to student. The teacher can send files to the student. The students can send files to the teachers. And I'll show you some pictures of real stuff that I collected. This computer screen, the teachers can see each of the screens of the student's handheld calculators. So it makes it so that you can see what they're doing. You can project it. It just totally changed my teaching when I realized what that was about. All right, so here is the TNS file for Fahrenheit to Celsius. And so, like I said, you can download this straight from the TI website, and I have all the links I'll kind of show you later when we get to the end. And they're yours now. You can edit them, you can add, you can take away. You want to just have the pictures, you can add pictures to it. There's a way to put questions in here. It really has, again, I keep saying it, but it really changed how I present my lessons, because it's no longer I'm just talking in front of the room, the students have it in their hands. So this slide is what the student's handheld looks like when you have 2 temperature sensors plugged in. And so in my classroom, I use what's called the lab cradle, and it's an accessory that my handheld fits in, and then the 2 sensors are plugged in. And there is a teacher document and a student document that are also downloadable that walks you through this entire process. each of the sensors, one I set to Celsius and one I set to Fahrenheit, and it doesn't matter which one you set. And then the type of data collection is going to be specific, and it's called events with entry. And so an events with entry means that once I start the data collection, and I will do that by pressing play, this little camera pops up and will take a picture or capture the data at that point, okay? So what I want to do with my students, this is what I do with mine, is I want them to collect 3 data points. I usually have ice. I'm in a traditional chemistry classroom with lab tables and stuff, so we always have sink and water. And then, so I want one that's basically just ice, maybe a little bit of water. The second one, I usually have a hot plate in the front of the room that has some warm water. And so one being kind of warm water. And then the third one, I want it to be, they're going to make friction between their hands, heat it up as much as possible, and then collect the temperature there. So this allows 3 data points. The ticket is that students have to remember is that both sensors have to be in the same spot at the same time. So I want both sensors in the ice. I want both sensors in the warm water, and I want both sensors in my hands. And so what data actually gets collected looks like this. When I press play and take a snapshot of the data, it records it. It was a trial 1. My Celsius was a 0. Fahrenheit was 32. My trial 2, when I snapped it, it was 15 and 56. My trial 3 was 100 and 212. Okay? So that's the data. And if you're unfamiliar with Nspire, this is called a list and spreadsheet. And so it works just like Google Sheets or Excel file. You can have in this, where the equals is, you can set functions and, different types of mathematical formulas. I am still old school that I totally believe my students should know how to graph by hand. So we really work on that in the first 9 weeks. Second 9 weeks, I teach them how to graph on the calculator. Third and fourth 9 weeks, they're doing it all by themselves on the calculator because the analysis part is really easier for them to do it. So from this data table, they can then send the data to what's called a data and statistics page. So if you insert a page, you can insert data and statistics, and it just plots the 3 points wherever. And so this is a teachable moment where you can discuss with your students, well, I just have 3 points. These 3 points mean nothing and until I assign my variables. So I ask them what variable should be on the x-axis, and they always say the independent. I'm like, okay, well, what was the independent here? Well, we only have temperature. The other had to be trials. So you can put trials, but because we're looking at Celsius versus Fahrenheit, we really want to know what's the relationship between those 2 temperature scales. So I'm going to start, and I'm going to put Celsius on the x, and then I'm going to go put Fahrenheit on my y. And I get 3 points, and it looks like a line, and it's really pretty. Now I have them do the analysis because I want them to get the equation of the line and then understand what that equation means. So under menu, which is where everything lies, we're going to go to analyze. We're going to run a linear regression. And then we get the equation of the line. We get y equals 1.81 x plus 30.534. If you are a chemistry teacher, hopefully you just had an aha moment that this is actually beautiful science. Stacey, you have great data. I fudged the data, sorry, to make it beautiful for you guys. But then I explained, the students and I talked, what is y equals mx plus b? What is m? Well, m's the slope, Ms. Tibb, you know that. Yes, but what does it mean? Well, it means rise over run. Okay, what is rise over run? It's Fahrenheit over Celsius. All right, it's also, we call rate of change. It's the rate at which Fahrenheit changes over the rate at which Celsius changes, which is 1.8. So every Fahrenheit, there was a Celsius change, and it gave us 1.8. All right, so then what is 30.585? 30.5. What is that? That's the y-intercept, Ms. Gibb. Yes, it's the y-intercept, but what does that mean? Well, that's where y is when x is 0. Exactly. So what does that tell you about the relationship between Fahrenheit and Celsius? When x is 0, Celsius is 0, what is Fahrenheit? It's 32, and we know that. My data shows 31. And the kids go nuts because they know that water, the traditional temperature scale of water is 32, it freezes. They now have the proof that if water freezes at 32, well then it's 0 degrees Celsius. If you flip it, hopefully you're like, I hope I get it, and you do. Again, my slope is not perfect, but it does give you the same relationship, that the 0.55 is the rate at which Celsius changes over Fahrenheit, and then this is the relationship between them. I am in Louisiana. We take the ACT as juniors, and it is 1/4 of our school performance score. So I really strongly believe how important data analysis and those skills are for the students to be successful on the science portion of the ACT. And TI technology can do that because all I did was 3 data points and took their math algebra 1 topics of slope, intercept, form, and had an entire conversation about Celsius and Fahrenheit. So you're like, why did you even do this, AC? Well, I did it as an explorer so they could learn what the temperature scales are to understand what the freezing and melting of ice and water are. This slide is a picture of the Navigator software when the students are logged in, and I had a dummy class, so I apologize, there's just one person, and that was me. The class logged on. This calculator 1, that was my calculator that I was collecting the data. And then it's kind of grayed out right now because I'm not on the software. I could click on that one student's calculator and click Make Presenter. The student now has control over the screen in front of them. They can then explain their data. What did they determine? I could lead a couple maybe. How did you get your y equals mx plus b? What does yours mean versus another? It's no longer, oh, let me take your calculator and put it under the document camera, or let me walk around and show everybody this person's graph. It's in the front of the room, and now it's the student's data that makes it so much more important for them that they feel accomplished when their data is projected and they're now the teacher. Again, another huge teaching tool that helped me, and I'm going to link all this back to how it is an NGSS solution, but I just wanted to walk through and kind of show you some things. So this is why I do the whole Celsius to Fahrenheit activity before I jump into this, the ice cream part. This is a typical phase change diagram that I use in my class. And so here for A, we have what a solid looks like. In the middle of C is what a liquid would look like. And over here is what a gas would look like. And I am big on, because chemistry is mostly numbers and symbols, kids don't necessarily understand what's happening on the molecular level. So we draw everything. We draw what we think is happening, and then we fix it to what is happening. So the next activity we're going to do, I make my students draw molecular level models of what is happening, because otherwise it doesn't matter that they can regurgitate what the temperature of water freezes is, because the standard doesn't attack that. It says to infer the strength of the intermolecular forces. A solid has lots of intermolecular forces. There's very little energy on this diagram. Energy is increasing as you go from left to right. So compound in A has very low energy. So those molecules are close to each other and they have a strong force of attraction. When I get to C, I have added temperature which is also adding energy, these molecules are moving around faster, so they're more spread apart. There's less forces of attraction. When I jump over here to E, these molecules are all over the place. They have lots of energy, lots of temperature, therefore they have very weak intermolecular forces of attraction. So this lays the foundation for the fun stuff, which is making ice cream. So why do we add salt to icy roads or when making homemade ice cream? So what we would do in a classroom is I tell the students this is your task now. So we did an engage, which was the pictures of the phenomenon slide that I showed. We did an explore explain. The first explore was Celsius to Fahrenheit activity. The explain was using that phase diagram with the conversation piece of the Celsius to Fahrenheit. Then we do another explore explain. This explore has to do with why do we actually do what we do with salt. So I give my students this, and then they go design their own experiment. I don't limit to what they can or can't do. Some students, what I've had in the past, carry this experiment over a couple of days, and I'll explain why. Some get their data right away, and they move on, and then they can do the analysis in class with me. So each student would have a CX handheld. They have Vernier temperature sensors. I usually use styrofoam cups, but if a student doesn't want a styrofoam cup, I have the regular, like bathroom Dixie kind of cups. I have beakers. They get all the ice they want, obviously. I would give them lots of ice. Always have water. And I just use table salt and table sugar and just plastic spoons. You could get fancy if you teach like an AP Chem or an advanced class and you want them to have other salts. Go raid your chemistry friend's closet to see what kind of salt he or she has and add other things. If you don't want regular table sugar and you want to try some artificial sweeteners, you can have whatever. So just in case anybody is not clear, this is called an easy temperature sensor. So it's easy in the fact that it plugs straight into the top of the handheld. And over here is how Vernier has the setup that works. There are other temperature sensors that don't plug straight into the calculator. You would have to have what's called an Easy Link, which plugs straight into the calculator. And I can get you more information for Eric if you have questions. And you could use a lab cradle like I did for the other. So there's actually 3 ways to do data collection. When I first started this, I asked one of the TI science guys, and I said, hey, I have a grant and I want to buy some sensors. What are your 3 favorite sensors? And when you ask somebody, what are your 3 favorite sensors, they're kind of like, this is a big science nerd. So his first one was a temperature sensor. They're not expensive. I think I would lie if I told you, maybe $60. A gas pressure sensor, and because I teach chemistry, the other sensors, I only have a few, are the colorimeters, because I also teach the Chemistry 2 class in AP Chem, so I have colorimeters. Gas pressure and temperature sensors, you can do a lot of chemistry labs without spending a ton on all the variety of sensors if you're starting out small. Okay, so then students would then actually go do it. They would go perform. If we were in the classroom, I would go over, if this was our first time using the sensors, which in the curriculum right now it would not be, but let's say this is your first time, I always demonstrate how to do everything instead of having them struggle on the technology. I believe in productive struggle. Struggling with the technology shouldn't be the main focus of this lab. It should be the understanding of the analysis part. So I always have my screen set up, and I show them how to navigate through everything. And so this is just a home page. This is when we would press or plug in what pops up. This is what once you're collecting data, this is what the graphs page would look like. And then once we're analyzing, this is what the data and statistics page or the data table would look like. So all of these that are in the top right and bottom right and then the bottom left are in the app on the handheld, which is the Vernier Data Quest app. So TI worked with Vernier to get the DataQuest app onto the handheld. So there's nothing additional if you're new to data collection with the Nspire. There's nothing additional you have to have for them to communicate. So sensors plug right in, and it's plug-and-play technology. When I plug the sensor in, this information comes up, and it's ready to go. You can change the mode, rates, durations, like we did the first one that I showed you. This one we do time-based, because we're going to look at the change in temperature over time and see if that's an indicator of why we would put salt on these different situations. So I would spend some time setting it up with them, and then they go about their business and they collect data. So this was my attempt of collecting the data. And so this picture or this slide is actually of a student's handheld. It says stop presenter, which means this was the student's handheld. So once the student would run the data collection, I would actually have them explain what they did. So when I do this lab, some students want to make an ice slurry. So they put 5 ice cubes, 20 mils of water, and they make a slurry of ice and water. Some take an ice cube, put the temperature sensor on the top of the ice cube, add the salt or sugar, and that doesn't give you very good data. Some students made an ice cube trays, had just regular water, made salt water and sugar water, put it in ice cube trays, and basically recorded the time it took to freeze, and came back and checked periodically in the classrooms, class times. None of those were ever dictated by me. So if you're an NGSS person or a 3D, you can kind of see where this is headed. This is totally student-driven. I just said you have to go figure this out. I did have some students, because of that first picture with the phenomenon, asked if they could do the boiling water part. Absolutely. I just pulled out beakers, I pulled out the hot plate, and instead they did the hot side of it, and then the others did the cold side of it. Is it chaotic? Absolutely. But it was student learning. As long as they were, not wasting materials, I was fine with that. So this is when the students would then explain, like I said, what they did, and I'll explain to you guys. This run 1, which is in the little, what are those, pentagons? Sorry. That was my control. So I just had an ice water slurry, temperature sensor in it, and I recorded 180 seconds of data. I could have changed it, but I just left it at 180 seconds. This is my run 2. I went ahead and did the salt before I did the sugar. And so it's red and it has triangles. And then this was my run 3, which was the same ice water slurry like I had for 1 and 2, but it had sugar in it instead of the salt. If you're new to how this DataQuest app works, you could change these different symbols. You could change the colors. I just do whatever's default. It makes life easy. It's one less decision I have to make in the classroom, but you could change all of these. So this data, right, what you see is in the DataQuest app. You can do some analysis here, and I'm going to show you how I do that when I go back to the teacher software. But you could do like we did a while ago when I sent it to a listen spreadsheet and then a data and statistics page. So you don't have to live in this app. The app does do a lot, but if you wanted to do the listen spreadsheet and data and statistics, you could. All right, so I'm going to go back to my teacher software. And so this is my lab data. Same data you saw, this is just now on my teacher software that, let's say, would be like projected. So the Explorer, they did it. Now they have some data. They really don't know what this data is. They know that there was obviously starting temperatures of the ice wasn't the same. So some students are like, hey, Ms. Tibb, can I redo this? I want them to be as close to all the same starting temperatures as possible. And I'm like, yeah, go for it. Absolutely. Some students, it doesn't bother them. They don't really, they're just like, I wanted to see the overall change. One of the caveats with this is that students must pay attention to this little grayed out check mark. If we were doing this live, what you would have to, what's called store your data in between each run. That's probably the number one thing that happens with students is they forget to store their data and they lose it. So then they have to redo it. But they only ran it for 180 seconds, so that was only like 3 minutes. And if they change that and it only did it for 60 seconds, it really wasn't that big a deal. So the first run I do with students, I'm like, okay, when you finish your first run, call me over so I can make sure you check the box, and then we move on. So let's say I wanted to do some analysis of this. My data isn't extremely beautiful. If I wanted to send it to a list and spreadsheet, I did that already because it's right here. I could then send that data to the data and statistics page, which at first you're like, oh my gosh, that's a whole lot of data. Remember, we took data for 3 different trial runs, temperatures, and had temperature data for 180 seconds. So it is a lot of data. So hopefully they listened the first time you did it when you talked about what the variables mean. And so in this time, they would need to remember that on your X should be your time. We have run 1, run 2, and run 3. So I'm going to put time from run 1. And they love that. They love to see those dots move, and they ooh and ah, and they're like, do it again. And so I go click on the Y, and I'm like, I'm going to put my temperature there. And then, bam, I get a graph of a line. And you can do that for each. If I go change, because my times are the same, I don't need to change my times, and just put each of them and then observe. I don't know what happened with that one. I don't know if I stirred it or what. That's a good conversation part, too, to ask students. So you have these outliers. What happened? Why did it drop so much and then come back to the top? So all teachable moments. So what normally happens with my students is just based on this graph, they can tell me what happened to the temperatures. We can see that the first temperature of run 1 was at 8.2, and the last was at 7.1. So they could subtract those two to get what was the average change in temperature. Not a whole lot. Sugar would be 8.2. I'm sorry, that's on the wrong one. Was 6.0, and then the last temperature was 5.0. Also, not very much. For run 2 was 4.4. We got down all the way to negative 1.8 degrees Celsius. But Ms. Thibodeau, you told us that water freezes at 0 degrees Celsius. I did, but my ice water slurry solution is not frozen. How is that? You're like, aha, that's what we're trying to get at. So why is it important to add salt when we are making homemade ice cream or when we have icy roads? And it's important to do that because of this picture, which goes back to that phase change diagram we talked about. This is the molecular structure and order of water. It is very ordered. There's forces of attraction between water molecules that keep it ordered. If I add energy to the system, aka increased temperature, these forces of attraction can be broken. It's now a liquid. If I cool it off, it becomes back a solid. When we have icy roads, we have ice. We have this nice ordered a setup here. When it melts, it gets all fluid. It's going to freeze again at night. It's going to come back here. We don't want that to happen constantly because it becomes slick. We had nice fluffy white snow. Now we have a flat, icy surface that's horrible for any kind of travel. So we add salt. This is what happens. When you put salt in water, salt does what's called dissociate, and it breaks up into its ions. And those ions actually get in between the water molecules. So if I have this mixture right here and I drop the temperature to 0 degrees Celsius, the same forces of attraction that happened over here at 0 can't, because I have a positive blue or a negative green sodium or chlorine stuck in the middle. So in order for it to freeze, I have to drop the temperature or remove energy from the system even more than I had before. The same token, when I add salt to ice when I'm making homemade ice cream, I want the temperature around that bucket to be as cold as possible so that the liquid on the inside becomes cold and a solid ice cream. The opposite with the hot water is that when the salt dissolves, it doesn't allow these water molecules to be in contact. Therefore, they're not touching, and it boils at a much lower temperature. If you're a chem teacher or you're a physical science or biology teacher, you've heard of this before. It's called colligative properties. You just taught them more about colligative properties of water, freezing point depression, and boiling point elevation with a lab and the TI technology than you could have with making them do all those calculations. So this is why I totally believe in what's happening. This just met that standard. Now, I have to preload some of the content because they have to understand what, phase changes are and what ionic compounds are and when they break up in water. But this was actually my assessment for this standard. This was their, in quotes, tests. So how does this all relate back to NGSS? So NGSS is the science and engineering practices, which we'll see in blue. The orange is what the content or what they should know. That's the cross-cutting, the disciplinary core idea, And then the green is the cross-cutting concepts, how students think, but also the same concepts that can be covered across no matter who or what class you're in. Some districts do what's called a gathering, reasoning, communicating. This is where my students would do the explaining, all right? This is the explanation of what the data was. So they're going to use information that they just got. They're going to use models to gather the data. They're going to use mathematics and computational thinking, even though they don't realize what they're doing. The reasoning part comes into play in their explanation. How are they going to explain to us what they saw? And then the communication is some model, some argument with evidence, some way to communicate that information. So what I do in my classroom, again, this is just what Stacy in Little Youngsville, Louisiana does. It's called a CER. It's called a claim evidence reasoning, which is the same thing as the gather reasoning communicating, but they have lots and lots of resources out there on CERs. And if you haven't done them in the science classroom, it is the best way to see if the kids understand at all what they did. I use it to replace old school lab reports. I do 2 lab reports a year, just in case they still do lab reports in college when my kids get there. This is more important to me than filling out some formal lab report sheet or worksheet. So a claim is literally a claim. What question or what are you saying will happen? So before we started this, I would have had my students document. We called that old school hypothesis, right? So what do you think is going to happen? And my kids would say that the ice with the salt is going to melt the fastest. Because they think we put salt on icy roads to melt it. So that's what they think, because we don't have that around here, right? The evidence then comes from the data. So whatever their data showed, that is their evidence. And it could be in graph form. It could be data table form. Sometimes I have them sketch a graph instead of, I don't need the graph that came in the calculator. They can just sketch it for me. If we did like linear regressions or logistic models, they would include that in their evidence. The reasoning is probably the hardest for them. That is, why did what happened evidence go to support or refute your claim? And usually, if it's at all possible, they would draw me a molecular level model of what they saw. So the molecular level model would be something like this, but hand drawn in their drawing art. We're a one-to-one school, so they use Google Draw and insert it into the document. You can't just put this at the end of the year. You would have to front load, right? what do molecular level models look like, have them do them as groups, then have a partner, and then have them individual. If you're new to NGSS or how this all works together, this activity, this is Stacy's take on this. When I first started hearing about 3D learning and NGSS, I had to wrap my head around how that would change my teaching and the student learning, because I wasn't taught how to teach like this, and I wasn't taught like this. So I had to figure it out. I think of a 3D standard like a bar stool or a wooden stool like this. The performance expectation is what the student should be able to do after the completion of set number of days. You choose the days. The performance expectation is determined by them meeting all three of the science and engineering practices, the cross-cutting concepts, and the disciplinary core ideas. So when the students are writing the CER, they're using the science and engineering practices because they did a lab, they analyzed the data, they made mathematical models, and they're arguing with evidence. The disciplinary core ideas, the properties of matter that they had to know to understand what salt does when it dissolves and what does it look like when water freezes or ice melts. The cross-cutting concept is a conversation about energy, that the more energy you remove from the system, the less times those molecules are going to hit, therefore the forces of attraction become greater, and then now they're going to make an ice. So this is just my little, again, like I said, my little take on 3D and what it looks like. And so I included this in there to show you what we did. I could get this done probably in 2 class periods. My class periods are 55 minutes long. So by the time they come in, settle, get all their stuff and all that, it would take 2 class periods. So let's say in an hour and a half, give or take some, we basically met this standard. We asked questions and defined problems. The problem was, why do we do this? We didn't do a whole lot of models as far as between systems. We did mathematical models, but that is not this science and engineering practice. We planned and carried out investigations. Their investigation was totally student-driven. I didn't tell them what to do or how to do it. We did analyze and interpret data. We do that a lot in class. So by now in the year, they're experts at that, and we use mathematical and computational thinking. That was, like I said, the ticket for me with the TI technology. I wasn't a very effective teacher before that because it was hard for every group to see everybody else's data. Now with Navigator, we can see it within seconds. We also constructed explanations. We didn't really design a solution so much, so we could, right? So we used table salt, which is sodium chloride NaCl. If you had raided your chemistry teacher's closet and maybe you found magnesium chloride works just as good, then have that conversation. So some of my students last year, I had one group who researched. Once they had the conclusion, they came up with a solution, and they wanted to see if I had those chemicals and try them and see if they lowered the freezing points. Because obviously table salt, sodium chloride, is not overly good for the environment, and that's not even what we use on icy roads. But they kind of figured that part out for themselves. So we could have designed a solution and maybe changing the chemical. Engaging in argument from evidence, this is probably the number one thing with the CER and the Navigator software with the students' data, is they have to give a valid explanation on why they did what they did, what they determined, and then the science behind it. And then obtaining, evaluating, communicating. The communicating part was the big part with the CER. That's a lot of SEPs just in one lesson cycle. I put what DCIs I thought we covered. We did talk a little bit about human impacts on Earth systems, and that has to do more with like water quality. A lot of my students brought up that if we add too much, does it affect the plant life next to it? Does it pool in ponds around the roads? Does that affect the fish or the birds that are drinking or living in it? So they had conversations about that. Definitely PS1A, structure and properties of matter. We pretty much spent all year on that in chemistry. And then possible solutions or design solutions, and I kind of mentioned all those. Cross-cutting concepts, like I said, those are the ones that should be across the board. Definitely patterns in our data, cause and effect. Students in my class also mentioned things like, what if we added 2 scoops instead of 1 scoop? How much would the temperature drop? How fast would the temperature drop? So if we had time, I was like, go figure it out. It takes you 3 minutes. Energy and matter, I mentioned, big concept in chemistry and biological systems to talk about that. And like I said, we didn't really do system models, and we definitely didn't cover structure and function. So last slide I gave you was just some information. Like I said, when I started with this, I had to wrap my head around everything and started with books. I read as many articles that would come out. The National Science Teaching Association is probably the #1 source if you're still new to it. The CER information, there's a lot out there if you want to start small. The way I do it in my classroom is the first 9 weeks they do groups, CERs. I rotate groups and they have work with different people. The second 9 weeks, it's a partnership. And then the third 9 weeks, they're by themselves and they have to do the CER. And the fourth 9 weeks, they're by themselves, but then there's a twofold part to the graded assignment. They have to do it, and then they have to give feedback to somebody else on what they did and didn't do or whatever, their explanation. So it's really a full circle of how the CER develops in the class, and I think it helps them truly understand the science. I also put education.ti.com. It's backwards. I have IT. I'll have to fix that. Sorry, guys. That is the TI website that I was on earlier that you guys didn't see. The activities, there are lots of activities on the website that were made by teachers, classroom teachers, TI science coaches that are tried and true. It's not some person that sits in an office at TI that said, hey, I think teachers should do this. These were teachers that said, hey, we need activities and let's try. So when I first teach a new content or a new lesson, I go to the website and I say, hey, what does TI have for chemical bonding? I look up intermolecular forces, and this was the one on the sweating alcohol. That's one of the NGSS lessons. But this intermolecular forces one could easily be used and adapted. This is what I was mentioning where they're downloadable, so I can download the files. When I download the files, they're mine now. I can edit them, save them for next time. If you're wanting to see what it's about, there's usually a video that's associated with it, the vocabulary or content, and you're like, whoa, that's not at all where I wanted to go with that, or this is exactly what I needed. It does have standards alignment if you're using textbooks. If you still have to write your objectives on the board or in your lesson plan, here's all the downloadables, so you can download it in one big zip file. There's a student activity that's a PDF or a doc file. That way you can edit the doc file if you want. There's a teacher notes. Teacher notes are amazing. Again, that's how I got started. I would download the teacher notes and I would study it and print. I printed it, studied it, wrote all over it, tried it on my handheld, made sure I worked out all the kinks, and then I was ready to teach it. And I had the information there. Like there's technology tips, especially when you're first learning how to use Navigator. Like how do I do this? All the tech tips are in there. There's some teaching strategy tips. And then also, like I said, the TI-Nspire activity, the TNS file. So that's all there. That's really how I got started. I would go there for all those things. The gather, reasoning, communicating, the next generation science standards are there, as well as the NGSS hub, which is kind of a repository for NGSS materials. Those 3 books by far were my saving grace. To figure out where the new standards came from, that was from the framework. The who behind the standards and what their thought process, that was a vision and plan. Vision and plan for science teaching and learning opened my eyes to the teacher I was and the teacher that I can be with the addition of the new standards. And then this article, 3-dimensional instruction, just It came out a couple years back, which actually went through, like I said, all of the beginning information. So I know, Eric, you were watching the chat because I was not watching it at all. I'll stop sharing if you want to take the ball. Were there specific questions that I need to address, or were you able to answer?
I believe we're all caught up on the questions.
Okay,
there
awesome.
were a few questions about sensor-based data collection on the 84 and SmartView, but I think we're in good shape.
Okay, thank you.
No, thank you. This was really, really interesting. Great to see the neat activities and resources as well. Great, and for the remainder of this session and for the upcoming session, we certainly invite you to share what you're learning today, both on Twitter and Instagram. And in the chat panel, there's a link to the certificate of attendance, and we will also send that URL via email shortly after today's events. And also in that email, there will be a link to a session survey. We really, really appreciate the feedback. That just helps us make sure that we are continuing to provide content and events that best support what you're doing with your colleagues and students in the classroom. After the session and certainly in the upcoming weeks, if you'd like some assistance with resources or just general questions, please feel free to reach out to 1-800-TI-CARES, and our Dallas-based support team would be happy to answer your questions and direct you towards the proper resources.
Yeah, Eric, I just put my email address in the chat window. I know it was on my first slide. Email is obviously easy for everyone, but I really, if you're interested in starting this in your science or middle school science classroom and you just want to know how to get started, if you're new to 3D learning, I would love to have conversations with people. I'm a big nerd when it comes to all this, obviously, if I'm doing this on a Saturday. But the dynamics of what it can do for your students and the way it changes you as an instructor, your life as a teacher is so much more happy and fulfilled because it's not, the students are learning and doing, it's not you giving all of the information. So I would love to help anyone. It just makes me so happy to share information because not only do I know that you as the professional are learning, that I know you're going to bring it back to your students, and then that benefits even more students, not just the 150 I teach. So thank you again. I appreciate it.
Awesome. And really, truly, thank you, Stacy, for sharing your expertise and your enthusiasm with everyone today. It's just really, really neat to see what you're doing with students. And thank you, everybody, for joining us here. And in about 15 minutes, we'll be kicking off our third and final round of sessions here at the 2020 T³ virtual conference. And we'll see you in about 15 minutes in one of the upcoming sessions. Thanks so much.
Thank you. Have a great weekend.